section 6.2. And looking at number 5. And they give us a substitution here, which is 1 over x squared plus 9 dx. And we're going to use u equals x over 3 as our substitution here. Because keeping in mind that if we were to just look at this on our own with our x squared plus 9, if we let u equal x squared plus 9, we'd have du equals 2x dx, which there is no 2x as part of this. True? Alright. If we let our u equal x plus or x over 3, okay, ultimately our du then would just be 1/3 dx. Since x over 3 is 1/3 x. So the derivative of 1/3 x would be 1/3. So ultimately that would be that. Now the question is, how in the world does that work in terms of simplifying this stuff? Well, ultimately we saw one like this earlier when we were doing our AP stuff, where we have x squared plus 9. If we were to divide, if you will, the bottom by 9, in other words factor out a 9, we could rewrite this integral as 9 here, and then we'd have x squared over 9 here plus 1. And ultimately if we redistributed that 9, we'd be back to what we started with, wouldn't we? Okay. And ultimately with that we'd have 1 and then 9, and then we'd have x over 3 all squared. And we did that technique as well. Instead of x squared over 9, we could write it as x over 3 all squared. And then from there, if we do our substitution, we can first take the 1/9 out of there. We can make this u squared plus 1. And then ultimately we still have this dx here to deal with if we do those two things. We replace the x over 3 with our u that we have. And then again we have dx to get rid of, and we know that the relationship between du and dx is right here. We know that 3 du then would be equal to dx. And so if we plug a 3 du in instead of dx, we'd take the 3 out in front, we'd have 3/9 out in front, we'd ultimately have 1/3 u squared plus 1 du here. Because again, we're replacing the dx with 3 du. And ultimately, taking the 3 out in front would give us, instead of 1/9, be 1/3. And ultimately now, this is a useful integral because this is a known derivative. So what derivative gives us, or what function's derivative is 1 over u squared plus 1. That's tangent inverse. So 1/3 tangent inverse of u plus c is our answer. Final answer though is that, with the u substituted back in there, x over 3. We're good to go. So ultimately again at this point, our only option here when we have something like this, that what we think might be a normal substitution here of a 1 over x squared plus 9, if we can't substitute the x squared plus 9, then we could recognize that it is very close to a known derivative that we have. Because if that 9 was a 1, then it would simply have just been tangent inverse right from the get-go. True? Right. But it's not exactly tangent inverse, but we can make it look like tangent inverse by making the correct substitution, which means we can make that 9 into a 1 by factoring it out. And ultimately we get a nice quantity there that we can substitute and still find the solution, even though our original substitution that we might have thought does not work. Questions on number 5? Next. Okay. And 18 we have the integral of tangent to the 7th, x over 2, secant squared of x over 2 dx. Alright, so bottom line here is this is certainly not a known derivative. Okay? So if we were to set out to try to figure out what we could let our u equal here, then we might want to recognize that if it was something to do with the tangent here, if we let tangent equal our u, the tangent sentence, then its derivative, tangent's derivative is secant squared, isn't it? Which would be good because ultimately we're going to have to write a u and a du. And we want that du part to look like that other stuff besides what we've made u. So if we let our u be tangent of x over 2, let's say, and again I'm going to tell you right now this may or may not work because you can see that there's ultimately two compositions going on here. We'll try it this way and see what happens here. So ultimately we'd get that as our u. And keeping in mind, if we did that immediately right off the bat, we'd have u to the 7th, and then we'd have secant squared of x over 2 dx. Just keeping in mind that when I have tangent to the 7th, that means tangent of x over 2 all raised to the 7th power. Okay, so it's that stuff raised to the 7th power when I write tangent 7 of x over 2. So bottom line is I need to get rid of this stuff still. I'm good with my u to the 7th. If it was just u to the 7th, that's pretty easy antiderivative. True? It's a power function. So let's see what happens here when I do my du though, see if I can get rid of that other stuff. Ultimately, if we use the chain rule here for tangent of this, we'd have secant squared of that times the derivative of that, which would be a half, times dx. And so that ultimately would be our du expression. And if you look at our du expression, how close is that to what we have here that we're trying to get rid of? Yeah, you just need that half out of there, right? So half is just a constant, so multiply. You got 2 du then would equal secant squared of x over 2 dx. And with that said, we could take that stuff right there and get rid of it by putting 2 du in. That stuff is equal to 2 du according to our sentence right here. So with that, we take the 2 out. We'd have u to the 7th du. And from there, we just get u to the 8th over 8 times 2 plus c. So our u part here would be tangent of x over 2 to the 8th all over 4 plus c. 2 and the 8 would reduce. That would do it. Questions on that one? On number 13, we have a definite integral this time. We have from e to 6 1 over x ln x dx. Right. And notice that each time that it's written with a dx on top, I just put 1 on top and put the dx on the side just to keep it straight. Right. So what might be a good substitution here, would you say? Well, yeah, u would be a good start. So what might be a good thing to let u equal? If we let it equal x, that really wouldn't change anything, would it? How about ln x? Why would ln x be a good choice? Because du then would be 1 over x dx, wouldn't it? And so therefore, in terms of my substituting here, and when we do a definite integral, I'm going to show you a technique that I didn't show you on Friday, I'm going to show you now. Ultimately, when we have this situation with a definite integral, when we do the substitution here, we'd replace the ln x with u, so that would be here. And then we'd also have a 1 over x dx, okay, which ultimately would just be du. So the substitution would just look like 1 over u du. And the ln x is the u. The 1 over x and dx are replaced by du. It's a straight substitution. Now, one thing that you don't want to do here is when you rewrite this integral in u, you don't want to put e and 6 on there because these are not u values, they're x values. So you have two choices, and you need to know both choices because it shows up in the multiple choice sometimes. And one choice is that you can just write it like that and put dashes on there because you're not going to do anything with them right now anyway. Okay? And I'll show you the other way on the side over here in a minute. But ultimately we do that, and then if we integrate, we get ln absolute value of u, which ultimately is evaluated on blank and blank. Again, don't write the e and the 6 because these are not u values. And then finally, when we substitute, we can do ln of ln x. Oops, I don't need that. Don't really need the absolute value on this part here. And now we can put in the e and the 6 here. Okay? So once we've put the substitution back in, now we can reintroduce those variables. And with that, then we'd have ln of the absolute value of ln 6, if you will, minus ln of absolute value of ln e. Use the fundamental theorem. And with this, ln 6 is just going to be just ln of ln 6. ln 6 is positive, so I don't really need the absolute values. We can just make parentheses. And then how about ln e? ln e is 1. And then ln of 1 is 0. So ultimately we'd get ln of 6, and that would be our answer. Okay. All right. Questions on method 1 for dealing with the definite integral? Again, ultimately, as soon as we make the substitution, we're not writing down those upper and lower limits again. We're just putting dashes in there, and then once we resubstitute, then we can put the numbers back in. All right. The other choice that we have here would be this. We could have rewritten this as 1 over u du. Again, same way, and then replace the limits with what the limits are equal to here. So ultimately, these are now u values here, our upper and lower limits. So if we take our e, if you will, and we put it in here and figure out what it is in terms of u, ln of e, u would be what? 1. Okay. And then if I do the same thing with 6, if I put a 6 in here, it'd be u equals ln 6. Alright, so like I said, in a multiple choice problem, if you had to substitute that integral, they might have this as a possible answer, because this would be legitimate. Okay? Because if you have it written in u, it's okay to have limits on there as long as they're values that are u. So if you translate your x values to u values, okay, then it's okay to write those limits on there. Okay? Questions so far? And ultimately, if you find that method more convenient, if you were to redo this and just do ln absolute value of u, and put in your 1 and your ln 6, guess what you're going to get? You're just going to get the same thing we got here. Okay. So really, in the scheme of things, if it's a definite integral, do you actually even have to resubstitute back into x values? If you do it this way, you don't have to. Okay? So ultimately, you get ln of ln 6 minus ln of 1, and ultimately we'd end up with ln 6. So I guess the question is, in terms of which method, okay, which one's best? Well, both. Okay, they both work equally as well, and ultimately you want to do whichever one you feel most comfortable with, I guess. Okay? If you don't want to bother translating your limits into u values instead of x values, then just do it this and get it back into x and then put your values in. Okay? Or if you want to translate them to u values, then you can do it with method 2. Questions on that one? What else? And 7, we have an integral of 1 minus cosine t over 2 all squared, and then sine t over 2 dt. And they ask us to use this as the u. If that's the case, then our du is going to be the derivative of cosine is normally negative sine, but we have another negative out in front. So ultimately it would be sine of t over 2 times a half dt. And y times a half, because the derivative of the argument here is a half. So ultimately, again, we're differentiating cosine. Differentiating cosine gives us negative sine, but since there's a negative out in front, that makes it back to positive. So that would be our du. And so when we do the substituted integral, we're going to have u squared. And ultimately, this stuff right here, this other stuff, is exactly what we have here for du except for the half. So if we let 2 du equal sine of t over 2 dt, we would have exactly what we need. We'd put 2 du in there and we'd be good to go. So with that said, we'd have 2u cubed over 3 plus c. And so therefore we'd get 2, 1 minus cosine t over 2 to the third over 3 plus c. And that would do it. What else? Right. And 17, ultimately that's going to be very much like this one. You have a ln x that you can replace with the u. It's on top. And then what's left? Isn't it a 1 over x dx?
It's like different though. It's like x on the bottom,
But it's x on the bottom. It's 1 over x dx,
no,
isn't it?
but the dx is like on the top.
The dx is always on the top.
But like 1 over x dx.
So 1 over x dx is what you have, and you also have ln x all raised to the 6th.
Yeah.
Right? So if you let your u equal ln to the 6th, Isn't your du going to be 1 over x dx like it was in that last one? This is your integral, right? So if you let u equal ln x, then your du is going to be 1 over x dx.
Oh, okay, never mind.
So ultimately your integral is just u to the 6 du, isn't it?
Yeah.
I'll let you finish it from there. Alright, what else?
What number was Ryan talking about?
17? 17. What? 11 looks very much like this one because you have a tangent that you can substitute. And what is the derivative of tangent? It's the secant squared one, isn't it? So try that one again. I don't want to do all of them because I want you guys to practice and make sure you can do it. So once you've seen one that's similar to it, see if you can follow those same steps and use it. Ultimately, your integral there is just going to be radical u. So u to the 1/2 is going to be your integrand there. All right. Next, we are going to work on a little bit more work with using this idea of substitution in the context of some more differential equations. And if you look at on your page 320 here, we have the title here is called Separable. When did you turn in your day 1 homework?
Oh,
I'll grab that one.
it's in my locker.
You can grab it. Just bring it back to me. So ultimately, this idea of a separable differential equation, we talked about this the other day when we introduced them in section 6.1. But ultimately, the ones that we had to do in section 6.1 were rather easy because ultimately all the ones that we did were just in terms of x on the right-hand side. So we just multiplied by dx and then we integrated and did our work. Now what we're going to look at today is some that aren't quite that easy because there's going to be y's involved in the differential equation as well as x. And as we saw when we did with our slope fields, and when we have a differential equation, it could be in terms of x, or it could be in terms of y, or it could be in terms of both x and y. And ultimately the question is, can we deal with all those different types in terms of finding solutions? And the ultimate answer to that is no. Okay? We can't algebraically solve all differential equations that we're going to be looking at here. And therefore that's why we have slope fields, because if we can't solve it with algebra and calculus, then we have to be able to draw the solution curve somehow. We're going to use a slope field to draw it, so at least we have a picture of it. We don't have an equation for it, but we have a picture of the solution curve, which ultimately is going to be something y equals in terms of x, which we can in turn use to make predictions. So with all that said, like I said, the techniques that we're going to learn are going to be only techniques that are going to work for what we call these separable differential equations. Okay? And there's a even broader term for that, which we don't really need to worry about right now. And I also mentioned too, this whole idea of differential equations is an entire class in college, not just a section or two here. So it's a pretty vast topic here, but we only essentially scratch the surface. Now, what it boils down to is if we are going to be given a differential equation, and it could look like, whatever, it doesn't really matter. We got a variety of them that we're going to look at here today, but ultimately if we have one like this one, then our issue here is, can we solve this differential equation? Well, if you remember what I told you the first time when we started looking at these, is ultimately we need to get the things with y with the dy and the things with x with the dx. Okay, and that's the separation of variables part. Alright, so when we separate the variables, our work is going to look like this. We're going to get this stuff that has y with it onto the other side, which means if this is a multiplication, which it is, we're going to divide. So we're going to wind up with 1 over 1 minus y squared dy over here. And over here we're going to have 2x e to the x squared dx on this side. So ultimately we've separated the variables. That's going to be step 1. And in the past, on the AP test, there's usually a separable differential equation problem on the free response. And if it's worth 9 points, this part's worth 6. So 6 out of 9 if you can do this process. Okay? So very important that we can. It hasn't been on every test, but there's in a lot of the tests in the past 10 years, there's been a question like this where every little part that you do is worth a point. And if you do all the points, you get 6 points, which is huge out of 9. Okay? So separating the variables is generally 1 point. So if you can do that, then you got 1 point. Okay? All right. The next part is to integrate both sides. And depending on how difficult the integrands are, this might be an easy step or it might take a little work. Okay, in this case, we need to look at the y integral and look at it and say, well, let's see. Is it a known derivative is the first question you should always ask. And so in our case, the answer to that would be what? We just had it a minute ago. Yeah, it's a known derivative. It's tangent inverse, isn't it? So ultimately on the left, we'd have tangent inverse of y. And then on the right, what about this? Is this a known derivative? No. Okay. However, if you look at this, and again, keeping in mind that if it's not a known derivative, and there's really nothing we can do with algebra to manipulate the integrand, then our only other choice at this point is substitution, because that's the only other technique that we know right now. True? So think about, is there anything I could substitute here where something might work out nicely? If I did x squared, notice the derivative is right here, isn't it? So conveniently, if I go u equals x squared, then du would equal 2x dx. And therefore my substituted integral, I'm going to do that on the side over here, would be e to the u now, and my 2x dx would just be du. Again, I got u is this, so e to the u is this part. I got 2x and dx, and I know 2x dx is du. So if I anti-differentiate, I'd get e to the u plus c, which ultimately would be e to the x squared plus c. So on the right-hand side, I would have that. And again, if you don't believe it, differentiate this. What would the derivative of e to the x squared be? It'd be itself, e to the x squared, times the derivative of the argument, which would be 2x. So wouldn't the derivative of this be 2x times e to the x squared? Exactly what we expected. So now, one question we might ask at this point too, which is a good question, is why don't we have to add c on the left side? When we integrated the left side, we didn't add a c, did we?
No.
Well, why did we on the right then? Anybody have an idea? Why don't we need it on both sides?
Does it have to do with something that x only on the, or the c only on the x side?
Nope.
That's what I was.
Let's just say we did add it to the left side. Let's say we said tangent inverse of y plus, we'll say k instead of c because it's going to be a different constant. So let's say we had plus k on the other side. And on this side we had plus c. Okay. Ultimately, what could we do with the k? We could subtract it into the other c, couldn't we? And what would we have on the right side now? We'd have some constant. True? So ultimately, what do we just call it on the right? We just call it c because ultimately it's just a constant still. Because if I have a constant minus a constant, what do I get? A constant. So I don't really need to write it on that side. And that works out nicely with the fundamental theorem that we don't have to have separate k's here because ultimately we're going to use our initial condition at this point if one was given to figure out what that constant is. And if it's in the form where there's only one constant, it's much easier to deal with. Okay? So ultimately we just have constant on the right only and that's it. Now the issue here that we need to I guess worry about next is this solved? Remember, ultimately the solution to a differential equation, to any differential equation, is the equation that this derivative came from. Okay? And in the scheme of things, what would be convenient is if this were an equation in terms of y in terms of x. So if we can solve it for y, we definitely want to do that. And in this case, ultimately, to get rid of tangent inverse, we just take the tangent of both sides. Tangent and tangent inverse undo each other, and we get tangent of e to the x squared plus c. Now in this case, they didn't give us an initial condition, so there's really no way to find c. Okay? Ultimately, we get a family of functions whose derivative is what we started with up above. Okay? All right. Now, question might be is there any way to verify that? Yeah, of course, we could differentiate that, couldn't we? Now, if you look at the way it's differentiated, though, or what we would do to differentiate that, is that we'd have to do the, of course, the outside function here would be tangent, so if we differentiated it, it'd be secant squared of the argument times the derivative of the argument, and so on. And you notice that in our derivative here, it doesn't have any secant squareds in there, does it? So the integration part might be a little tricky, but it probably could be done. Let's try it. So if we do it, if we differentiate and we say dy dx is equal to secant squared of e to the x squared plus c, and then the derivative of e to the x squared plus c is 2x e to the x squared. No. So this would have been all 6 at that point. And usually it's an initial value problem, so this probably would only been worth like 4, I guess, but if there was initial value, you'd have found C and then found the ultimate equation. Alright, so bottom line here is this is what it would look like, right? Okay. And with that said, okay, if you look at this part right here, this has 2 to the x e to the x squared. That's the same thing we have here up top, right? And that part, I should say. Here's your 2 to the x e to the x squared. That's part of our derivative here. But what about this?
What was C like? Like, is a C defined at all?
Possibly.
What if it was 0? Or
Question is, how do I get from this, which ultimately, like I said, it has that part, and then these two are in common, but ultimately it has something in terms of y here, doesn't it? Okay. All right. So again, differentiating this being our derivative here, and this being our derivative, are these two things the same? Okay, in other words, is that is secant squared of e to the x squared plus c, is that equal to 1 plus y squared? That's what our conjecture is, isn't it? Just keep in mind, again, that's the part that's related to that, because like I said, these two parts are with one another. The 2 to the x, or 2x e to the x squared, those are there. Ultimately, we need to account for this part. So again, the question is that a true sentence here in this problem? Well, should it have to? I mean, ultimately, if what we did was right, okay, it should be true that those two are equal.
well, we're obviously not wrong. So
Right.
I'm gonna say
Well, let's put it this way. What does y equal in this case? Again, keep in mind, the issue here is that if we did our integration right, okay, then they do equal each other. They'd have to. Otherwise, this wouldn't be true. True?
would we just substitute the y for the tan to the x?
Well, let's see what happened if we did that. Keep in mind, all we want to do is show that these two are the same. If I did that, if I did 1 plus, and I did tangent of e to the x squared plus c, all squared, I'd have that, wouldn't I? So, what do you say? Are they equal? And if so, why?
Yes.
Well, we know they are, 'cause I told you they are, but
Like,
Why?
what if you differentiate from the y?
Because you found out what y equals and then
remember, one of our Pythagorean identities is sine squared x plus cosine squared x equals 1, isn't it?
Right.
And if I were to take that known identity and divide everything by cosine squared, by the multiplication property of equality, I would have tangent squared x plus 1 equals secant squared x, wouldn't I? Isn't that one of our Pythagorean identities? And what does this sentence say? Isn't that exactly what that says right there? That right there is secant squared of that argument, isn't it? Okay. So again, keep in mind that tangent squared of any argument plus 1 is equal to secant squared of that same argument. And isn't that what I have here? This is tangent squared of this argument plus 1 equals secant squared of this argument. So, can you in fact differentiate it and show that it's correct? Absolutely. Okay. So it doesn't always, depending on how difficult the functions are, might not be completely obvious of what to do right away, but ultimately, you know, using the information that you know is true, okay, you can use substitution, etc., and get to the derivative and show that it does in fact equal our original, which is this. Okay. Alright. Let's take a look at page 322. This is an example here. We're going to look at number 40. Whoops. Do that. So we have another differential equation. This is x radical y cosine squared of radical y. Right. And so we're going to solve this differential equation. And again, if we do separation of variables, we get that x on the same side here. Ultimately, on in terms of the y part here, we would move the y stuff, if you will, onto this side with a dy, and leave our x dx on this side. Alright, so with that we would have our variables separated. Again, the y information on the left, I'm going to divide it, because it's on top on the right, so it'll be on the bottom on the left. And then the x stays as is. We multiply both sides by dx to get the dx out of there. And now we have something that we can integrate. So, the integration part, you know, on the right side is pretty easy. X dx is x squared over 2 plus c, so we're good to go there. But on the other side here, okay, we have radical y cosine squared y on the bottom here. So the issue is here, and again, this is clearly not a known derivative. So our next technique then is there anything we can use for substitution? Can we substitute?
Square root of y. Or no. Well, cosine squared.
Well, if we did cosine squared, though, we're going to have to differentiate cosine squared of radical y, which is going to be pretty ugly.
No,
Right.
square root of y.
So that's probably not the right choice. You know, you could try it and you'd find that it doesn't work. But you know, ultimately, if you did square root of y, okay, ultimately your du then would be, keep in mind this would be u to the 1/2, so it would be 1/2 u to the negative 1/2. So it would be 1 over 2 radical y dy. And notice what do we have in here? We have a 1 over radical y right here, don't we? And our dy right here. So let's think about what that substituted integral would look like then. We'd have 1 over cosine squared of u. And again, keep in mind we'd have a radical u and a dy here. So we have everything we need right here in our du statement, except for we have a 2 right here, which means that a 2's got to go. So if we let that be 2 du equals 1 over radical y dy, then we could replace the radical y in the dy, because again, this is 1 over radical y, this is dy. We could replace those with what they're equal to, which is 2 du. So that means that I have 2 out here and I have du here. Now, that's all well and good, but now we have 1 over cosine squared u. Is that a known derivative? Isn't that secant squared?
Yeah.
So is it a known derivative? Yeah. It's antiderivative. That's just simply tangent, isn't it? So we'd have 2 tangent u on the left, which ultimately we'd translate back to 2 tangent of radical y. And now we'd have x squared over 2 plus c on the left. So this is where we'd be after we do the integration step. We're here. And again, in this particular case, it takes us a little bit of work to do the integration on the left-hand side. Okay, we need to use substitution to do that integration, but ultimately, when we get that integration finished, then we have our next statement, which is the integrated version of the two sides, if you will. Alright? So the question is, are we done? Nope. Because ultimately, what are we trying to get by itself? Y. Trying to get y by itself. So if we divide by 2 would be our first step here, so we'd have tangent of radical y equals x squared over 4 plus c. No problem with that. Why don't I have c over 2? I divided everything by 2. So what's a constant divided by 2? Constants. Okay. And then from here I want to do tangent inverse of both sides, so I'd have radical y equals tangent inverse of all that stuff. And the final step would be square it. So we'd have tangent inverse of x squared over 4 plus c all squared. And with that, we will have successfully solved that separable differential equation. Alright. Questions so far?